Hey everyone, my name's Ty, and this is going to be a much different talk than I usually give, mostly because, as you might be able to tell from me speaking, I've come down with what I'm calling the speaker plague, which is mostly just mean my voice is shot. So I'm going to try to get through this. It's going to be kind of an experiment. If I do, awesome. If not, then I do have a recording of this that I'm going to be posting so you guys can kind of finish out the rest of it. Like I said, my name's Ty, and I've been working on Android since about 2009. And for the last 5 years, I've been focused a lot more on external developers with Android and working on developer platforms. This started when I was at Evernote and started working with their DevRel team on their open source SDKs and authentication, doing hackathons and stuff. Then I went over to Twitter and worked on the Fabric suite of SDKs. Did that for a few years, and now I run a small team on Uber's developer platform, mostly our external API, focused on the mobile integrations. For those of you not really familiar with what a developer platform is, it's kind of the arm of a bigger company that usually focuses on their external API, their developer tooling and docs, their SDKs, partner integrations, DevRel, and that sort of outreach. Or for smaller companies, it may be their primary product. Today, I'm going to walk you through some ways of thinking about these platforms and building them, as well as designing user experiences that make sense within them. I'm hoping that this knowledge will help guide you in building your own platforms on mobile, or if when you're just integrating against the existing ones in the market, that you would have a better idea of what's going on under the hood. So a traditional approach to mobile integration, and one that's historical roots lie more in sandboxed environments for apps, looks something similar to this. You have one web service and multiple apps that are installed on the device. Each one of those bundles an SDK or has code implemented to hit an API. They're doing a lot of duplicate data across the different third-party apps that may live on the device. They may be making the same requests, doing the same auth, caching the same data. As we start to think about a global audience, and one where the challenges of emerging markets are a little bit different, for example, in some markets, users pay by the kilobyte for their data usage, that duplicate data can become problematic. So I like to think of a more interesting approach where we can utilize some of the interesting features that Android gives us and think about how we can provide some of that first-party experience through the first-party app that may already be installed on the device to third-party apps that exist and that would want to consume data without necessarily having to duplicate network requests or various other state. And this preserves some of those issues and those constraints that I called out, but it also unlocks an interesting mix of functionalities for the end user, potentially. So I'll walk you through a few of these. But first, I'm going to cover a few major topics within these today, and I'm going to give you a quick overview of what they are. We'll start with a deep dive into thinking about deep links. This will be relevant for both Android and iOS developers. And then I'll cover some tactical approaches to thinking about designing, implementing, and simplifying mobile authentication between apps. And finally, I'll cover some more advanced inter-process and inter-app communication by discussing a deep system integration with our API. So let's start with the recent project, deep link support in the rewrite of the Uber Writer app last year. For those of you not familiar with deep links, it's a general term used on Android and iOS to represent a URI that an application can handle. In our example, the third-party application may want to initiate a ride request on behalf of the user. And so they would want to start the ride request flow within the Uber app. And the URI itself is just made of a series of parts that communicate the intention of the deep link. In this example, we have a scheme that indicates that it's for the Uber app. We have an authority to indicate the specific action that we want to be handled. And then we have additional metadata that's supplied in the query parameters, like the pickup location. Then we just register that URI in our Android manifest in an intent filter, and now the system knows that our app can handle opening that link. In the specific example here, I tightly scope the authority to write request. I don't just specifically rely on the scheme Uber here. This is to limit the scope of what could be handled. Potentially, we would want different activities that may sit around to handle different flows. But since deep links are a general term used across platforms and the web, it's more standard that you would see it used as an HTTP or HTTPS URL in the wild. And since this is called the universal link, and because it's just HTTP, it can't exist anywhere. So there are some flows that can become problematic. Let's talk through those. Maybe a user sees your universal link somewhere in the wild. Maybe it's an app, maybe it's on the web. But they say, hey, that sounds interesting. I've heard of this app, or that action that they're prompting sounds cool. I want to do that. And they click through. And their app wasn't installed. So a typical flow is that maybe you would land the user on a landing page where you upsell them, or you would take them directly to the Play Store or the App Store to try to get them to install the app. And they think to themselves, hey, that was an interesting use case. Yeah, I'll follow through on this. Then they open the app. Maybe they have to walk through an onboarding flow. And while that's maybe a bit annoying, that's not exactly what they were wanting to do initially, they're still intrigued by that use case that they clicked on, so they follow through. And then guess what happens? Your app didn't preserve the user's intention, and it just drops them in your standard home screen. What happened to that link that they clicked? Well, the context was lost. They're going to have to duplicate their effort. They might have to leave the app and come back or manually navigate it within the app. But that's fine, right? No, of course it's not. Since it lost track of what the user was doing, their first emotion that's associated with your app is probably going to be frustration. And that's really not what you want invoked. So that brings me to an important design principle in thinking about these inter-app integrations. That's you should always strive to preserve the user's context. You should do everything in your power to keep them from having to redo a specific action or duplicate effort. The more seamless you can make this flow, the higher conversion rates you're going to see. So how can we think about solving that user's problem? Because we're using a standard HTTP URL, the browser will handle opening this. And we want to provide the best possible experience here to our end user. And more commonly, that requires that we do get the app installed. So when we land on this mobile web landing page and we try to upsell the app, we're going to want to do a few things. We're going to want to record the original URL that the user was trying to go to. And then we're going to want to send that user to the Play Store with the refer query parameter indicating the specific URI that the user was trying to go to. Now, when the user installs the app and they open the app, there's a broadcast that's emitted from the Play Store, and that's going to contain that refer query parameter. So this is your opportunity to grab that and then continue that flow for the specific user. But with Android Marshmallow 23 and up, Google introduced this thing called app links, which makes this a little more seamless. Prior, if you clicked on an HTTP URL, you might say that Uber can handle this, but also Chrome can handle this, and Firefox, or any other thing that can handle an HTTP URL on your device. But with app links, Google allows you to indicate that you're the default app to handle a specific URI to provide a better experience for the end user and to provide a better security model. To implement app linking, you just need to make a couple modifications. One, in your manifest, you want to indicate the auto-verify tag here. You want to say that this is true. And then what that means is that for URIs, HTTP and HTTPS URIs defined in that intent filter, the Android system is going to try to check if it can handle it for you. Secondly, on your web service, you would want to host a file called an assetslinks.json that contains a copy of your public fingerprint of what signed your application. Now this means that Android can see in the manifest that it's supposed to handle this URI. It can query your domain, it can see this file, it can see a copy of your public fingerprint, it can compare that to your APK signature, and it can say, cool, this is the real Uber app, we can allow them to handle Uber links. But an interesting caveat to note about app linking is that if you have multiple intent filters defined in your manifest, even if only one of them uses the auto-verify tag, if they are indicated as browsable and an HTTP or HTTPS URI, the system is going to assume that it needs to auto-verify them as well, even though the tag didn't exist. And if any one of them fail in your entire manifest, then it's going to say that it couldn't verify, and it's going to revert to the old behavior where the intent picker is shown to the user. So while deep links can be pretty powerful, they can also spawn a slew of unique problems for your users. Here's a fun problem that we ran into earlier in the year while trying to deserialize some query parameters coming into the Uber app. Does anyone that's not an Uber employee here care to take a guess at what's going on? Good guess, but no. No. With this specific case, I'll show you the URI that was causing it and the bug in the code here. So here we have a lat long, and here we're using the number formatter to get a double value out. Now there's a very subtle bug in this decimal parsing logic. We were using the default locale, and lat long is always indicated to be broken by a decimal, even in locales where a comma is traditionally used for numbers. So if this was in Portuguese, for example, where it was expecting a comma, it would see this decimal, and instead of throwing any sort of number format exception, it would try to give you a valid number from that. So we ended up with like a mini million lat long. Unfortunately, this hit a bug further in the route rendering logic, since we had a valid pickup. It was using the GPS, which was valid, where it just wrapped that rendering around and around again. Of course, you couldn't request that. It was problematic, but it did take a very subtle data validation bug and kind of push it down the chain where it was much harder to debug. As you can see with that previous example, when relying on other apps to tightly integrate against the contract that you require, it becomes difficult to know if they've implemented that correctly. And there are many ways in which these integrations can break down. And when they do, it's often because the integrator didn't do something as you expected. And you might think to yourself when this happens that it was the fault of the implementing application because they didn't go to your spec specifically. And technically, you might be right. But to the end user that had this frustrating experience, they don't know where the problem broke down or why it broke down. They just had a bad experience and they're frustrated by it. So as the platform provider, it's always your responsibility to try to ensure the best possible user experience, regardless of how the user ended up in your app. So let's look at how we could implement that principle. Here's a user flow through the ride request deep link that I showed earlier. This is a simplified version of it. Here we need to make many decisions on how to continue and make sure that we have the right state in place before we can request a ride. When the deep link comes in, we need to find out if it has the right action that we're trying to do. Is it a ride request deep link or is it something else? Maybe if it wasn't, we just take the user to the default landing page. Then we need to validate some of the data that came in. Does it have a valid pickup? If not, maybe we can use the GPS. Does the pickup have a name? If not, maybe we can geolocate that based on the lat long. Then we move over to the destination. Did it have a valid destination? If not, we leave the user in the UI where they're traditionally trained to input their destination. We do the same thing for the destination name lookup. Finally, we check if a valid product ID came in. And for those of you not familiar, the product ID in the Uber data model is just references essentially like an Uber X or Uber Black or the different types of products that you might see in a specific market. So if it has one set, potentially it was requesting an Uber Black. The deep link was, but you're in a market where Uber Black doesn't exist, so it's invalid. So we need to handle that state. Or perhaps one wasn't included at all, and so we just need to use the default or let the user choose. And finally, we need to take the user to the place where they can confirm that this is actually what they're wanting to do. They need to trust that the system is working, but we need to preserve that trust by allowing them to confirm this sort of flow. And since we open sourced our RIP architecture yesterday, which is a cross-platform architecture that we use for the base of our apps, I wanted to show you a bit of the implementation, and this is again a simplified view of that. But this uses our workflow tool, which exists within the RIB library, to describe a deep link. And this navigates our RIB tree. So we could start at the root, and then for each one of these steps, they could potentially wait for user interaction or a specific thing to come back. Like the wait until signed in would wait there if the user was logged out until they finished that onboarding experience, and then it could continue. We could navigate down the flow with to ride and then to trip, and we might get to a state where the user clicked a deep link for a ride, but they were already on a trip. And so we need to handle some failure cases. We maybe need to abort the flow early or show the user an error. But if not, then we can continue. We can set these pickup in the destination. And for each one of these methods, It's an implementation on the interactor in our RIB architecture of an interface that we're calling an actionable item. You'll see that in the workflow library that we open sourced. And so it allows us to have this clean, descriptive language of navigating a user through a very complex set of steps based on a deep link. And this allows specific changes to be made in those interactors that are less prone to breaking this flow. So I've got you thinking about some of the ins and outs of deep links. So I'm going to move on to the next topic of discussion that I want to go over, and that's authentication. It's a pretty common mobile developer platform feature to integrate authentication to call certain endpoints for your web service. It's usually a requirement for most APIs. And we understand that it can be really scary for a user to look at a screen like this and see that an app wants their personal data, maybe their location, or even the ability to request a ride on the user's behalf. And when we were reviewing the mobile auth space, while we were thinking about our own auth messaging, we could see that there's hardly one standard approach to this from all of the big platform providers. Many of them iterate with different experiences, trying to make it more seamless for the user, trying to be more transparent for the user. And so as we thought about our own experience that we wanted to provide, we were driven by another value, although a pretty basic one. That's when it comes to your users' trust and privacy, you just need to do the right thing for them. Consider what's in your user's best interest, give friendly messaging, be transparent, and explain the ramifications of the data that they're sharing. Allow the user to dive in for more details when they want, and provide approachable use cases while trying to stay away from legal jargon and too much verbosity that might confuse or scare a user away. And expect clear opt-in from the user. Now, while we want developers to be able to get up and running with our authentication as quickly as possible, the Uber API also has both regular and privileged scopes, depending on the impact of that specific API. For a regular scope, like getting an estimate from one location to another, using implicit grant in the OAuth spec is probably perfectly fine. But for requesting a ride on behalf of the user, we want to implement something that's a little more secure. And for that, we implement the authorization code flow spec from OAuth. And this is a lot more complex for the end developer to take into account. It starts with a client app that contains a client ID, and they initiate the authentication with the Uber OAuth screen. And so the user would approve that, probably. That would return back an authorization code to the client app. The client app would then be responsible for communicating that code and up to their service where they're hosting a client secret. That web service would then combine the auth code and the secret and communicate back to the Uber web service to exchange that for a valid auth token that could then be used. And then it would return that back to the client app in the end. And as you can see, this process is a lot more involving for the third-party developer. And it can be a little bit more off-putting for people to integrate against, and we wanted to improve on that. Fortunately, that's something that's been done in many of the apps that you use as well. So native app sign-in or single sign-on is a concept that you've probably used, like Facebook Connect. By integrating against the installed Uber app on the device, we can use the Uber app as the guarantee of that second part in the authorization code flow. To the end developer, they have a very similar flow to the implicit grant. They just request an authentication with the client ID, and they receive an auth token at the end. But there is more complexity going on that's just abstracted in the Uber app. Internally, we would use JWT encrypted payloads to communicate up to the Uber web service and authenticate the user, all doing that within the process of the Uber app on the device. So there's a few ways I've seen single sign-on built out in mobile before. The most straightforward approach is to have a third-party app call a URI that your app is registered to receive, and on completion of the flow, you call a redirect URI that their application is registered to receive. But another approach that I've seen implemented is to use intents and custom actions to do start activity for result from one app to another. And then that finishes and it provides the result back to the calling application. Some problems with this, it's specific to Android, and it's not that discoverable as well. It has a bit of a higher overhead for implementation. This is actually the way that the Twitter app and SDK was implemented for Twitter auth because of handling legacy partners that had been out in the wild for a while and needing to keep some consistency between opening that solution up to the public market and those partner integrations. Another approach that's similar to the second approach is to use the Android account manager to implement authentication on the device. And this This last integration is the platform ordained one. This is what you'll see in the Android developer docs. But it's unique to Android again. And it requires additional permissions on older versions of Android. And it's pretty hard to implement. The docs aren't great. The sample code is complex. You'll be pulling your hair out trying to implement this one. But I will dive into this and why you might want it in a little bit. So using URIs and callback URIs is the most standard approach in my mind. And there's even an IETF RFC out that's standardizing this both for iOS and Android for doing native app sign-in. The idea with this one is that we launch this URI, and then similar to the deep links, we check if the app is installed. If the app is installed, then we say, cool, we can go over and we can do app auth. But if the app is not installed, we say, do we necessarily need app sign-in? Is this a non-privileged scope? If it's a non-privileged scope, we can do the implicit grant authentication in the browser in the client's application. But if they do require privileged scope, then we're going to require authorization code flow. And if they have that set up, we can still do the browser authentication because they have the server designed to handle that code exchange. But if they don't have that, and we do have privileged scopes, then we probably want to do a deferred deep link install that we covered earlier to upsell the app to the user, and then continue that flow after the user signs in. Finally, granting user approval, we can return that authentication token back to the end user. Now, as you can imagine, when authenticating users, security should be a very high concern to you. Firstly, I recommend that both sides of an integration specify the package that you're communicating with so that other apps cannot try to intercept it. To further enforce a secure communication channel, I would also recommend that you get the public fingerprint of the applications that you're trying to communicate with those, and then you indicate that programmatically in your app integrations. For our Uber developer dashboard, we collect the public fingerprint of your APK as part of the setup steps so that when we're returning a result from the application, we will only communicate with your app if we know your app is signed by a key store that you indicate is valid. On the SDK side that the third-party app integrates, we also include a copy of our public fingerprint of the Uber app. So when they're initiating the flow, it's only talking to the Uber app and not a malicious app that might try to sit in the middle and fish for credentials. The fingerprint is pretty easy to retrieve. You can use KeyTool on your key store. You can also use KeyTool to get it off of your APK. Oftentimes you want to do it off of the APK because you might not have access to your key store if it lives on a CI machine doing releases. Once you have that public fingerprint, you would just put that in whatever platform you were indicating, like the Uber developer dashboard. Or if you were provide your own wizard for a UI, for a user to implement that. And here's a common approach that I've seen to checking that in the clients. You'd use the package manager, you would query for the signatures, you would then check if that public fingerprint exists in the list of signatures. But does anyone see an issue with this code here? All right, well, let me give you a quick visual of the trust chain that the key store uses to sign your APK. You have a root CA and a number of intermediate CAs, finally your developer certificate. And when you sign those, they're all going to have the same public fingerprint all the way down the chain. And if you, so there's a reported vulnerability called the Android fake ID vulnerability that has been reported many years ago, I think it was 2013 or 2014, where a malicious app could be signed by a malicious key store that would pretend to be validly signed, but it was not actually. And the previous code that I showed didn't properly handle that. This would take the public fingerprint of an app. You could take an APK, you could take the Uber app, you could take Google Maps, you could take whatever. And you could say, what's the public fingerprint? And then you could write up a quick Python script to generate out a malicious key store where the entire chain just looks like this. It doesn't go up to root. Obviously, the fake Uber CA and the malicious cert are signed by different public certs. So it's problematic, but Android wasn't handling that. So in later versions of Android, they did fix this, and they implemented Google Play Services fixes as well. But on older versions of Android that still exist in the wild, or devices without Google Play Services, think like old Amazon Kindle devices, it's still potentially a security hole. So it should be accounted for in this SDK and authentication code. And it's a very simple fix. instead of checking if one signature matches the public cert that you expect, you just check if any do not. If any do not, you know that you're dealing with a malicious trust chain, and you want to abort the flow. So let's move on to a different implementation, one that I used when I was working at Evernote for authentication, and that was the account manager. Now, if you're looking to go to a darker place where you can understand some of the deeper Android-ordained ways of doing this, I'll give you a quick walkthrough of the account manager and how we built it and why we needed to use that over the URI approach. Specifically, we were integrating with Samsung, and they needed to have explicit account access that was exposed. And the account manager does do that. It puts it in the account screen of settings and provides APIs that make it accessible. If we didn't have that requirement, we probably would have done the URI approach. But why am I being so hard on the account manager to begin with? Well, to start, like I said, it's an Android-only approach, which is great for you folks here, but most teams are multi-platform. Their PMs like to think for Android and iOS features, and it becomes a hard sell to tell a PM that you need weeks to implement a very Android-specific feature that doesn't have necessarily parity with your iOS counterparts. Second, the implementation is arduous at best. You'll spend a lot of time looking at sample apps and blogs and tutorials and trial and error before you get this working. It is pretty complex. And lastly, for older versions of Android before dynamic permissions, it did require get accounts and manage accounts, which means for many of those devices, they're still out there, it's going to block an auto-update path, which is going to be really problematic for your users getting onto an updated version. So if you're still with me, let's cover some of the basics of it. Some of the benefits of this and why you might want to use it are that the account is easily accessible to other applications on the device, both through the API and for the user. It also provides helper methods that those apps can interact with to do things that you might want, like refreshing an OAuth token, getting at the token, seeing how many accounts are signed in for that specific app, access to night scenarios, and more. And finally, it does provide a level of user experience consistency when the user can come to this one screen in their settings and see that they have all these apps that they signed in on their device, as well as they can indicate that they want to sign into an app through the overflow menu here. So that helps a little bit. So how can we track our own app, their account here? Well, we'll need to work with two classes to do this. The first is the abstract account authenticator. And this is a service that the account manager communicates with. The account manager is running on the device at the system level. And the second is the account authenticator activity. And this is the activity that you need to extend and write code for that is your sign up and sign in onboarding flow for the end user. Now, this is a diagram explaining one of the common steps, which is get account, which is get auth token taken directly from the Android developer docs. Here, an implementer would get the account, if it exists, based on the package name. They would call get auth token. When they do that, you would go into your implementation from the account manager, proxy to the service. And if you are signed in and you're in a good place, you can return an auth token to that application. Maybe you're not signed in. You could then instead return a pending intent with information on how to start that account authenticator activity so that the user can go through your sign-up flow. And when that's done, it will return that data. And this also handles some of the error use cases and handing those back to the consumer as well. So let's walk through a few of the important implementations of this process. Add account is called when the user wants to add an account explicitly for your application. So this method is called when they click that overflow menu in the general settings screen and click add account. You'll want to return a bundle with the information on how to start your authenticator activity so that the system account manager will proxy that pending intent and start that activity for the end user. And we would set the activity in this bundle, and then we would just return that. Get auth token is another interesting implementation, and this is one as a consumer of your platform that they would be using most of the time. They would get your account first, and then when they call get auth token, if you're in a good place, here it's a very naive approach where we're just holding on to the username and password to do authentication with our web service. In your implementation, I would recommend doing an authentication token instead. But if we are in this valid authenticated state, we can make our API request and we can ask our service for an auth token for this third-party app. But if we're not, maybe we don't have an auth token, then we need to handle an error scenario where we want to, this is actually where once we get the result back, we hand it back properly for them to consume. And then we get a little further down and it's an error scenario where if we didn't get the auth token, we may need to prompt the user to log in. So we need to handle the similar flow that we did through add account, where we populate information on how to start a new authenticator activity. Now, when we're adding a new account from our authenticator activity, each application will have its own custom authentication flow, right? Which is why you've implemented this activity. But at the end, we need to handle a few common things for the account manager by hitting its API. So first we need to create the account based on the username and the account type. The account type is usually the package name of the application. If we're adding a new account, then we also need to explicitly add it to the account manager here. And then we want to set the auth token that was returned from that flow into the bundle so that we can return it to the calling application. And then we can both finish this, we can set the results in the authenticator flow as well as ending it traditionally for the activity. And that will return the user back to their previous flow with a valid auth token, and they can continue making requests up to your API service. Now, all right, enough about authentication. I hope you can see why the account manager implementation is a lot more complex than the URI approach. Let's move on to our last area of discussion, and that's lower level direct inter-process communication. So when Samsung worked with us at Uber and they wanted to build their own personal assistant on the Samsung devices, Bixby, they wanted to be able to have it request an Uber. And that required some back and forth communication from Bixby and the Uber service. And so we brainstormed this approach with them, and we had a few different suggestions and ideas. At first, we thought about using the web API. You know, they could just include our SDK or hit the APIs directly. And this would allow for a great range of use cases without client-side changes in the Uber app at all. But unfortunately, it required the user to OAuth. And this was a non-starter for Amazon because because on iOS, ride intents are treated as a first-class citizen, and the user can just directly go from Siri into taking a ride. And they wanted a very similar behavior. They didn't want the user to have to authenticate, and then the potential concerns of a user revoking those credentials, and then the Bixby client being in a weird state. So second, we thought about using deep links, IPC, or a content provider to communicate back and forth between Bixby and the Uber app on the device. We could create an API for each use case they needed, maybe start a ride, get information on the existing ride, etc. And while this would work great when the user's already logged in, it would require additional maintenance to the app. It would couple that version of the app with Bixby, and it would be very hard to maintain going forward. Think about deprecation or versioning of those APIs. So the solution we settled on was a mix of the two. It was to use an IPC, which we'll get into shortly, which with an internal service to hit Uber's external API. But as opposed to building one API per use case, we treated it as a pipeline so that we could make general requests that were authenticated against our API. And this managed the authorization token for the user, since it was in the Uber app properly. And it allows for the app to stay pretty stable in its APIs, since it's not specifically implemented to those specific use cases. So first, how does IPC work? First, you would want to define an Android interface definition language file. It's like an interface, but it has the AIDL extension. And Android allows you to define these, and it'll generate a stub for you that you need to implement on a service and then bind to. And once you've bound to that, you can communicate with it directly from outside the process. And this can be used from across applications or just between processes in your own application if you need that use case. And it allows you to directly call methods on it, which can be really powerful. But the sender and the receiver both need to implement the same concrete implementation. And all the primitives and the types that are going across need to be parcelable. So let's go over a sample implementation of the project that I just showed. Here, we're going to create a lightweight AIDL file. And this can just receive a GET request. First, we define the file and the method, and the type primitives here. The type and the primitive here are what we're communicating across. So the type needs to be parcelable, like I mentioned. Next, we would implement that auto-generated stub from the AIDL file. Here, we're going to validate that the client ID coming across is one of these like whitelisted Samsung type that can actually make this request. We wouldn't want anyone making a request on behalf of the user without a much deeper sort of validation. So if it's a valid ID, then we can go ahead and we can hit our own external API with that information that they communicated to us. And if not, we can return some sort of error state to the app that was trying to make this interaction. Next, we need to expose the remote service by returning the binder in the onBind method, so that any consumer who attaches will receive the implementation that we designed and implemented. Now, the service will cache the results of onBind for the life of the process, so expect the same value each time you call it. If you return null because it wasn't ready, then that's going to be cached and you're going to not be in a valid state, and that could be very problematic. So finally, with that implemented, we can consume that remote service in another application. We can communicate to the Uber API. We would set up a service connection, and this receives callbacks for both service connected and disconnected. And then we need to initiate the binding and the unbinding of the service through our normal lifecycle methods. Now, one interesting thing about onService disconnected is this is only called when the remote service that you're connected to has an unexpected exception. So in your on pause or on stop, however you're handling your destruction of this, you need to explicitly unbind the service and null it out. But once this is connected, we know it's connected, we've had the callback, we have this implementation, and we can safely make requests to the service in the Uber app, and we know that we're going to get valid data. So this was a minimal look into how we built out client-side proxy for Bixby. And this also preps some interesting ideas for building platforms in the general community where you could have apps that are acting as data pipelines for other applications. And so with that, that wraps up the last major topic that I wanted to talk about. So to recap a few things, when we're thinking about building app-to-app integrations, it's easy to go wrong and end up in a bad place that's frustrating for your users. I think if you consider some of the values that I talked about, you could end up in a place where instead the experience you provide is greater than the sum of its parts. And specifically, you should try to never make the user redo any actions by preserving the context that they initiated. You should always take responsibility for the user by having experiences that degrade gracefully and friendly messaging to help guide the user when there are issues that they need to resolve. Lastly, when it comes to things like data privacy, a user's trust is of the utmost importance. So provide friendly, approachable, and transparent experiences to guide them through otherwise scary experiences. Lastly, although these systems can be very rewarding to build out, debugging them can be very challenging. In my experience, many integrations are device-specific. You might see this often in cameras for specific manufacturers that have an AIDL that you want to integrate against. So setting debug points here and switching back and forth between applications can be really problematic when you're developing. So with that challenge, good logging is going to be really crucial to helping you fix issues that are going on. And setting up automated integration tests with mock implementations of your consuming expected APIs is going to be really critical to automating anything that might break this. Unfortunately, not all of these APIs are discoverable. Android doesn't have a great way for an app to just say, what are all the intents that this other application are providing? Which of them are public? How should I use them? So having accessible developer documentation and communication channels with your developer community is going to be really important to making these successful. Now, these integrations can feel like magic when they work well, as I've said, but when they cause a lot of frustration for the user because maybe the app integrating against it didn't implement set result properly or do something else that may not be the most straightforward, You want to have a good line of communication with your users so that you can understand what's working and what's not, what apps are working in the space and what are not. Think of ways to seek user feedback, even consider a beta channel. And lastly, rely on great tools for collecting broader amounts of data. Use analytics, crash reporting, things like that, so that you can understand how these integrations are doing in the wild. I hope you had some great takeaways from this talk today. And I'm excited to see more apps that exist on Android that integrate with each other. I think it's a really powerful feature that Android provides that's underutilized. If you want to see some of the other integrations that we've done for Uber, feel free to check out our developer site. If you'd love to work with this sort of thing, my team is hiring, as well as all the other Android mobile teams probably at Uber. So feel free to reach out or DM me if this is interesting to you. And I have about 5 minutes for questions now. If not, then I will be around after and you can come talk to me. Yes?
I've seen or read in various places about third-party apps being able to pull Uber pricing, kind of real-time pricing information through accessibility services. Is that true or allowed, related to what we're talking about today?
I'm not familiar with that at all, using the accessibility services. Okay. I'm sorry. All right, everyone. Thank you.